is called downscaling. So when you hear, that's good, thanks. When you hear about downscaling, that means you take a big model, calculate what is happening at the edge of the box, break down what is happening at the edge of the box, break down again, then you know what is happening in this box. So depending on what you want to do, you use different kinds of models. So these are very, very computer intense type calculation. Now people actually have been doing this for a while. So what you have is time and global, all these things are happening now. So this is the mesoscale, as I told you, that is the local weather, about 100 kilometers. So when you say that the western part of Sri Lanka is the weather, this is the kind of model you run. The whole area covering Sri Lanka, this is the kind of model you run. If you want to go to climate, it becomes much more difficult. So the question is, you run this model or this model or this model, you run for that particular type of phenomenon. What is happening on 10 meter scale? What is happening in 1000 meter scale? But the question comes, now this is about 7 days. Seasonal models are months. Now the question is, if you have something in between, none of these models can pick up that. Because each model has a specific purpose. So between, let's say, seasonal scale. Now seasonal phenomena, what is that? Monsoons. It's a season to season. Okay? Now you have synoptic, which is the day-to-day weather. So typically it's a 7-day type models. So between a 7-day prediction model and a monthly prediction model, there are certain things this modeling system will miss. So those are called intra-models. So in this case, it is called intra-seasonal. So intra-seasonal means between 2 seasons. That means between a season and another season. That means it involves synoptic scales. For season to season is months. This model predicts on days. So between days and months, what is happening you don't know. So in between, what you have will be intra-seasonal scale. So if you want to predict how the monsoon starts, you know that the monsoon keeps on churning for a while. So if you predict for 7 days, it's not good. For monsoon scales, not good either. So if monsoons are starting, that is in between, something between the two, that's the intra-seasonal scale. So this is the reason this new project dealing with intra-seasonal scales, because it is between 2 seasons. What is happening between 2 seasons, which are not picked up by either weather model or a global time model. So this is actually is a problem which has to be solved. Not even trying too much. But one thing is that, remember, this sun is about 1000 kilometer scale, months. This is 7-day scale. So if you want to do an experiment to find out what is happening in between, then you have to have the experiment at least run for months, several months. You have to have measurements over thousands of kilometers. So it's not a simple thing to do experiment here, but you need 1000 kilometer scale to get something to understand what is happening in between. So that is the challenge. So you need observations, but observations exist, probably you know, that satellites keep on measuring over and over again. Every day satellite has at least once over a given spot. So per day you have at least one observation over Sri Lanka, let's say. And that satellite will give you regular observation. And you know the Met Department, they send the radio sondes, maybe about once a day. In Sri Lanka about 4 times a week, but once a day. So you can see daily observations coming from satellites and also from radio sondes, from the Met Office, Met Department. So that gives you things to worry for years you are measuring, but once a day. But there are some phenomena which is happening much more details because you cannot see. So you measure 12 o'clock today, 12 o'clock tomorrow, but you don't know what is in between, so you cannot understand very well. And also, satellites are pretty good because it gives you a global coverage. But the problem is the time coverage. So what we need is some observations that can be taken, let's say, every 3 hours. Can you see what is happening every 3 hours so we can follow the development of something? Okay? So we are going to attempt that in this situation. So one of the things actually why we are interested in the tropics. Now you are in the tropical ocean from -30 to +30 latitude, right? So this is a project which is going on now, which is called the Coupled Model Intercomparison Project, which is going on now. It's an international project called SLAFAR. So this model is comparing one model. You know that there are how many models you have? About 29 models running climate simulations. Different governments, different agencies, but these are 29. There are 29 which goes into IPCC. Okay? So different models, what they do is they take the different models and compare how they perform the prediction. So in this project, they have different types of norms. For example, here, they say, okay, the Earth's temperature in 100 years, if it changed by 4 degrees, what will happen to radiation? What will happen to the rainfall, precipitation? So that's what they want to know, whether each model gives a correct answer. So if different models give different answers, how can you believe any of them? Because if you want to predict in 100 years, you don't know what will happen. But if 4 models says 4 different answers, that's not good. Okay? So this one, it gives you a hypothetical scenario, and then you run the model and see what that affects. So here, 4 degree increase of temperature over the world, so it's a hypothetical, and see how does precipitation change. So here you can see 4 different models. So these are different countries, some is from Germany, and this one I don't know where from. So these different models. You can see this white color. It shows that about very little change of precipitation for these 4 different models. Remember, it's looking at the same thing, but see whether they are predicting the same thing for other parameters. Okay. Now here you can see the poles. Polar regions, you can see the precipitation is about 2.5 millimeter per day. It changes. They are consistent, 4 models. Now you can see the equator. The change of precipitation here, it says more than 3 millimeter per second, and here it says there's no change. So you can see even 4 different models, climate models, cannot agree with each other. So the question is, can we believe this? Obviously, I don't think you are going to believe climate models, but this is the state of the climate model. Right? 4 different models predict 4 different things for equator. For other regions, it looks okay. So now you see why we are interested in the equator, because equator is the place where you have a lot of problems in models. First, we are interested in rainfall. Second, we are interested in good prediction. Both of them are not doing a very good job by the global models. So, also this kind of shows why we should be putting a lot of emphasis on equator, right? Because other places we are doing okay. So now, this is the equatorial region. Why equator is so chaotic? And give all these different answers by different models. But we know that equator is the area where it's very, very highly energetic because you have a lot of sunlight coming in, solar radiation, the temperatures are very high. So the color represents the temperature, sea surface temperature. You can see the poles colder. Here is very, very warm. So when you have this, you can see a lot of they are getting warm and they rise So warm air rising is called convection. So a lot of convection is happening. Some of them, like let's say Indian Ocean, very, very warm compared to Atlantic Ocean. You can see it's dark red and it's a little bit lighter red. So here you have much more heat coming to Indian Ocean or stored in Indian Ocean compared to Atlantic. And also you can see Western Pacific is also quite warm compared to Eastern Pacific. So what will happen? When you have very warm surface, sea surface, you get a lot of air rising, warm air. And then when you have a little bit less warmer, the air rising and then it is coming down. So what happens is Indian Ocean, especially Western Pacific, air rising quite a bit. Some of the air goes up and going into the Eastern Pacific, and then it keeps on falling down, and then you have a circulation. And again, part of this rising air comes to Indian Ocean, and it keeps on going around. So this is called the Walker circulation. It's a very important process in the topics, Walker circulation. Areas where are warm, too warm, things are rising. Area a little bit colder, things are falling down. So the areas which are rising are called the intertropical convergence zone, where the air coming in and then they go up. So this intertropical convergence zone, you can see you have a lot of